Alright, today we will be presenting on queuing simulation. This is Session 2, looking at the Dagpunar textbook of Monte Carlo simulation. And just to give a little background on how queuing stations work, it's pretty simple. Basically, there is a service offered. So, for example, someone is offering ice cream to somebody. And we have different inter-arrival times. So between customers, say 1 and 2, one arrives 7 minutes after opening, one arrives 5 minutes after opening. And the inter-arrival time, therefore, is simply 2. And for these customers, there is a line that can hold people. So the customer that comes in at 7 minutes may have to wait in line behind the person that came 5 minutes. And there's also a mean time to service people. So we'll have a way of knowing how long it will take to service each person. And we'll also have a set number of serving stations. And then once that entity has been served, then they will exit and no longer be part of the system. And to generate some of these, we have multiple distributions that we can use to generate this. Usually there's a mean that the service time and the inter-arrival time work around. For example, we'll be using the Weibull distribution for one of our examples. And also there are different simpler distributions such as the uniform distribution where they're all equal, and the triangular distribution where it's basically shaped like a triangle with the mean at the top. And there's some different laws that govern queuing systems, and one of them is Little's Law, where we can easily calculate the average number of entities in the system by basically taking the arrival rate, which would be customers per unit of time, so customers per minute customarily, and the average service time, which is just the amount of time that it takes through our given distribution for a entity to be serviced. And one of the ways that queuing system can work is as a GG1 queuing system, which is basically a three-phase method. And how this works, there are three ABC steps. First, there is the advance of time from one discrete event to the next. So as I said before, customers arriving 7 minutes after opening, and there's a customer in front of them that arrived 5 minutes before. We don't necessarily care about the 6th minute while the service is going on, so we simply have the events at 5 minutes and 7 minutes where they both arrive, assuming that they are not serviced very quickly. And then we have a bound state change execution. So for example, if the second entity that arrived at 5 minutes is done being serviced at 8 minutes, then that person will leave the system, and that will be the action that takes place. And then lastly, our C step is the conditional state change execution. So since that customer in front has left the system, the customer in the queuing line waiting to be serviced can step up to the line to order their ice cream, and that will be a step for them to begin their service time that will take them to get served and get their ice cream. And for example, just to put a word picture onto it, without the ice cream example, is a clock moved up to the next eventful time, so as I said, from 5 to 7 minutes, and then say the next arriving entity appears in the system would also be a possible state change that happens, a bound state change in particular. And then lastly, the conditional state change would be looking at every other occurrence that happens at 8 minutes that goes on right there. And we saw in the example that the person steps into line after the person in front of them has been served. And to look at this in MATLAB, we can simply run this code here from my friend 2, where we have a lambda for the customers per hour, the rate at which they arrive, and the service time that it takes. So here we can see that more customers are coming in. The lambda is greater than the mu. Therefore, our line will most likely be increasing. And running this code, we can see that that's true. We can see the line length increasing over time, as well as the time in the system per entity. And just to give some validity to Little's Law, we can see here through our simulation that the average waiting time was about 18 minutes, and that was just about the same according to the calculation by Little's Law. So there we see a little bit of code. And another example that we made was simulating a hospital ward. So in this case, it's a little bit different. For the service time, we have a Weibull distribution instead of a Poisson distribution, which we'll be using, and we'll also have the possibility of walkouts. So if somebody comes in to a specific room and is looking for a bed to be serviced at, they may not be able to, so they'll be admitted to a different ward where they'll be sat down there. So there is the possibility of a walkout, so we'll be able to calculate that. And for this example, we'll be looking at a 2-bed example where there are 2 different beds and an arrival rate of customers, and we'll just observe how many walkouts happen in this case. So looking at this, what we have graphed for you is the arrival time and departure time, which are overlapping where they come together right there. As you can see some intersections, that's when the arrival and departure time are at the same time, where we see that both beds are taken up and therefore they cannot be serviced at that time at that specific part of the hospital. And for this run, we have 12 early departures, and that's simply due to the fact that we have arrivals coming in and the service times different, so that makes it difficult for each person to be serviced, and therefore some people have to be admitted elsewhere. And in this case, we can also increase the number of beds. How this works is it's a conditional statement, seeing if the time of arrival compared to all the other departure times is greater than the number of beds minus 1. So if there's an extra bed right there that they can be serviced in that's available. So running it with 4 beds gives us a lot better chances of them being able to be serviced, and as we can see, the number of early departures goes down to 0, and from our chart we can see that each person is being serviced and the distance between the two, sometimes great, sometimes very small, just based on the distribution that we have. So that's just a look at some queuing simulation going on. Thanks for